Okay, we're going to look at tutorial 1 question 3, but before we do, let's have a quick look at this bending moment and shear force diagram. You will note that the shear force values here are indicative of the slope of these equations. So we have a positive slope. If you remember, we've drawn our bending moment diagram with moment positive in the downwards direction. So this is actually a positive slope. It's going upwards, even though it's going downwards, because our downwards is upwards, or downwards is positive. So this is a positive slope here, which is indicated by a positive constant slope here. And at this point here, that slope reverses, and it's a shallower slope. It's 5 minus 5, so it's a negative slope, which means it's going upwards on our diagram, or downwards in the sense that our m is negative in the upwards direction, but with a shallower slope, and that slope is this minus 5. So we've got a plus 15 slope down to here and a minus 5 slope up to here. So if we just remember then, and we've discussed this, that if you differentiate the bending moment diagram, you get the shear force diagram. So if you come up with the slope of this line, that's positive up to this point, flips over negative, and then carries on at that value to the end here. Okay, so bear that in mind for when we come to look at the cantilever, which is the next question, and this is tutorial 1 question 3. In tutorial 1 question 3 we have a cantilevered beam with a uniformly distributed load, which is 10 kilonewtons per meter. So we've got a small w this time, a force per unit meter. Okay, so let's draw the shear force diagram first. We know that this reaction here must equal, so the shear force here, reaction here, V, is equal to 10 times the length. The length is 4 meters. So we get 10 kilonewtons per meter times 4 meters gives us 40 kilonewtons. And that is the value of the shear force here, V. So we can draw our shear force diagram straight away, and we can see that because we've got this UDL, this shear force going in this direction, which is positive, reduces incrementally by this uniformly distributed load until we get to come to here, where we've got 10 times 4, which is 40, balancing our 40 in the upwards direction. So this starts here at 40 kilonewtons and then comes down to 0 at this end. Okay, let's try and draw that better. It's actually quite hard to draw on this tablet, but we end up with a shear force that peters out to 0 at this end of the beam here. Okay, and starts at 40 here, 40 kilonewtons. This value here. Okay, if we now look at the bending moment diagram, where we will draw the moment positive in that direction. So we have a bending moment which starts out here. This bending moment here must equal, if we take moments about this point here, we have got 10 times 40, sorry, 10 times 4, and then we can say that that's acting halfway along, so we'll multiply that by 2, which gives us 80 kilonewton meters. So we start off at 80 kilonewton meters of bending moment, and we can see that the gradient, if you remember, the gradient of our bending moment is the if we differentiate the bending moment curve, we get its gradient. So its gradient starts off steeply and then ends up being 0. So by here we're flat, okay, and at this point here we're at our steepest point, and we can see that this is a UDL, so it must be parabolic. So we end up with a bending moment diagram that's parabolic. Let me draw that again somewhere here. We have a moment here, and this is the end of our beam here, and we end up with a value at 80 here and a value at 0 here, and that is a parabolic equation curve which starts off at 0 gradient here and our steepest gradient at this point here, which is from this 40. Okay, that's 80 kilonewton meters of bending moment. This is our bending moment diagram. Okay, and this is our shear force diagram. Okay, and in the next video we will look at question 4, which is the first of the truss questions.